So my name is Kaz, and this is Dennis, and welcome to our presentation. So transparent materials such as PDMS and glass are used in a variety of industries today, from biomedical applications to consumer electronics. So the desired characteristic of these transparent materials is the ability to see through them, but this also happens to be a downfall when trying to measure them, as it is almost impossible to quantify these materials using optical measurement techniques. So we partnered with FocalSpec to present you with a novel method to accurately and precisely measure these transparent materials on an inline manufacturing environment. So first, let me give you a brief overview of the presentation today. So we'll be starting with a brief introduction about the actual technology and the system that we used to do these measurements. Then we'll touch on the two applications which we developed for this product. So keep in mind that these applications are just the tip of the iceberg for the potential that this measurement system has. Finally, we will end with some conclusions and future work that we will be doing, and then we'll be happy to answer any of your questions. So as previously mentioned, our project consists of creating new applications for FocalSpec's LCI-1200. So this project includes components from a wide range of engineering fields, including software engineering, sample engineering and fabrication, including nanofab and cell culturing, as well as statistics. So there are two types of projects that you guys will be seeing today. So there's one that comes from more of a theoretical, science-based approach, and you might not be seeing this in industry for another 10 years if you even do see it. And then on the other hand, there's one that has the most impact on today's industry right now. And our project is the latter, one that will directly benefit industry as soon as it leaves our hands. So as you can see from this chart here, many optical systems fail where the LCI-1200 does not. Most importantly, glossy, transparent, and 3D images. So this chart does not cover physical measurement systems, but we will be touching on that later in the presentation. So first, let me give you a brief introduction on what the LCI-1200 is. I would encourage you guys to come see our booth later, and we can give you a real-time demonstration of this instrument. So essentially, it takes white light and breaks it into a continuous spectrum of wavelengths. This spectrum is focused onto the sample, and depending on the Z height of the sample, a specific unique wavelength will be focused, and the resulting reflection wavelength will be picked up by the optical system, and from that we can correlate this to the respective Z heights. So that's a brief overview of the actual system, but that is not the basis of our project. So we actually made this whole system with a variety of different components. So first, of course, we have the LCI-1200 as described in the previous slide. Next, we wanted to mimic a manufacturing environment. So to do this, we have a linear guide, the 1D stepper motor, and sample stage. So the sample stage is obviously to hold the actual sample, whereas the linear guide and 1D stepper motor are used to mimic an assembly line fashion. So we can stitch together the 2D images to make 3D images. So next we have a power circuit to power everything. We have our API software, and here we can start and stop measurements, adjust parameters, and view the actual 2D profiles. And next we have the MATLAB software. So this we use to analyze the results we got and get some hard data, so actual numbers for the width and depth of our samples. And lastly, we use Cloud Compare software, which is a 3D point analysis system to get some visually appealing 3D images. So not only have we demonstrated that this works on a working prototype, as you guys can see outside, but we have also used statistical methods, as outlined here, that are widely used by the manufacturing industry. So again, this drives home the value in our project. So at the end of the day, when a manufacturing industry is wanting to buy a quantification instrument like this, they're going to be looking at these three parameters: repeatability, GRR, and correlation. And so if they find that this system can satisfy these results, then they are going to want to buy this instrument. We will be touching on these one by one later on in the presentation. So our first application is to measure actual PDMS microfluidic channels. So these have applications in a wide variety of industries, from fuel cells to more biological or biomedical devices. But as previously mentioned, they're very hard to measure, to quantify due to their softness and transparency. So to make these samples, I'll give you a brief overview. We had to first make silicon master molds. So to do this, we spun photoresist, used photolithography to develop the resist in our specific patterns. We used deep RIE to actually etch away the silicon wafer where the resist protected components of the wafer that we did not want to be etched away. Finally, we had our silicon master molds. We poured the PDMS on these molds, cured them, baked at 80 Celsius, and we peeled them off for our resulting PDMS channels. So here you can see we made 10 different, samples, each with 10 different widths from 10 to 100 microns. So this came with our mask fabrication. And then we have 9 different depths, also in 10 micrometer increments. And this we did by leaving the samples in the RIE chamber for differing periods of time, so more would be etched away. So here you can see an actual image of our sample over there on the far right. So this is where most people stop with this kind of technology, at visual inspection. So how do we translate this qualifiable data into more quantifiable XYZ measurements?
I will answer that question. So in order to translate, so as Kaz discussed, this technology actually uses a chromatic method and actually gives you accurate 3D data in XYZ coordinates. So what it does is a 2D line profile. So what we can do is we can integrate the sensor into a linear stage to stitch together many 2D profiles into a 3D picture. And that's exactly what you see on the bottom right picture. You can see many profiles. And then you can actually clearly see the channels on the bottom. And what we can do next is extract these profiles into MATLAB or whatever computational program that you want, and you can produce quantifiable depth with radius or whatever you want to do, right? So this is the advantage of XYZ data versus a visual inspection. So as I said, showing the capability of a sensor is one aspect. The other aspect is making sure that it actually works, right? Because a lot of projects can write papers and papers of theory on how it might work, but not show actually how it works. So to show that it works, we did 3 tests, like Kat said. The first one is correlation. Correlation, the purpose of this is to show that whatever you're using can correlate to something that you already trust, right? In this case, we use DECTech. We use DECTech for a couple of reasons. First, it's a physical stylus, so it is not prone to any visual aberrations or any interference patterns, right? So you can actually have physically whatever is on your profile. So we correlate it to DECTech, and when we were actually doing this, we had a really difficult time doing PDMS because PDMS is actually elastic. So the tips will actually get stuck in the PDMS and drag the sample, right? So we weren't expecting this. So instead, we actually used the silicon molds to measure on DECTech. And as you can see on the bottom right, the correlation curve between LCI-1200 and DECTech from a span of 10 microns to 100 micron feature is 99%. So what this tells us is that we have confidence in this machine. Another interesting thing that we learned as we did this experiment is if we had PDMS that weren't measured, we wouldn't be able to measure them, right? No optical profilers could do it, and DECTech can't do it. So without this system, we wouldn't be able to measure it. So secondly is repeatability, right? This is something that manufacturers look at heavily. It's how repeatable your data is. So if one operator does 1,000 samples a day, can they reproduce the same result again and again, right? So repeatability is calculated by using the standard deviation of your sample divided by the expected value. So usually in manufacturing, it's expected within 10% variation, and we can show well within that expectation. So beyond that, it's a more comprehensive Gage reproducibility and repeatability study. So this actually comprised of 90 data points for each specification. So we did 90 data points for width and 90 data points for depth, right? So it has a couple components in it. The first component is variation due to equipment. So this is when you fixture, when the sample stage is moving, how much noise does your entire system bring into your measurements, right? The second one is appraiser. So this applies to the operator. Can different operator throughout the day measure the same thing again and again, right? This also depends on your system. And the third one is total reproducibility and repeatability. And essentially each component of this is a percentage variation due to that specific component out of the total variation, right? So in order to have a good study, you want parts that span very large variations. So what we use is 10 microns to 100 microns in depth and width. And that way you can sort of see the percentage variation in each component. So once again, all the specs pass by what is the industry standard, right? So what this data essentially tells you is they can take the system and implement that in their manufacturing line today, right? So another interesting application that I want to explore is cell culture application. This has never been done before. So the primary goal is sort of to measure cell confluency. It's how much cell you can see on the given area, right? And the secondary goal is, which is more interesting, is a apoptosis study. Just to go into a little more about apoptosis. Apoptosis is essentially cell death. What they're having to do now is to measure apoptosis, they have to stain the cells. And staining the cells actually is a terminal process. So that ends essentially the cycle for that sample. So for any drug study that requires studies for 2 hours, 4 hours, 6 hours, you're going to have to make separate samples for those because after you stain it, they're done, right? But if this is successful, we can actually measure the intensity changes in the cell, and that way we can one sample and measure it how many times you want, whenever you want. And this would be really revolutionary for cancer research or any drug research. So to find a good way to quantify this, we measured different confluencies of cells, right? We made samples at 0%, 10%, 50%, 90%. And we measured them on the LCI-1200 with the linear guide to have 3D pictures. So visually, it's difficult to see. There's a lot of noise. In order to quantify it in a proper way, we use surface roughness. So surface roughness has many parameters. SA is only one of them. SA essentially is the average height of your surface, right? So we want to see if there's a correlation between confluency and surface roughness. What we expected was when the confluency goes up, the surface roughness will also increase. But we do not see that here. So I think that tells us it's very difficult to get the cells. So our results, our conclusion is that we actually can't see the cells. But we have two sort of ideas of why it didn't happen. First, because the roughness of the polyethylene glass substrate is similar to the roughness of the cell. So that's really difficult to see. And secondly, it might be an optical because the cells are really small and transparent. So it might be really hard to pick it up. So just a couple of conclusions. So these are the sort of machines that we kind of approached to compare the system that we built. So DACTAC AFM, they're both physical statuses, which is a huge challenge for elastic materials, as well as 3D metrology. For a physical stylus, actually can't do any 3D. It's only a line profile. And for optical profilers, yes, you can do a 3D image, but you cannot do transparent or high slope because the focal distance is actually really limited. So you actually can't measure something that's really sloped. And also high aspect ratio parts are really challenging as well. So for future considerations, I think for PDMS, first of all, we can try to build more complex geometries. For example, you can build depth of channels that's varying within the same channel, and also obviously differing scanning speeds. And for cell culture, there are a couple of things we want to try as well. I think first we want to try a non-reflective growth substrate. So use a matte black substrate that can optically distinguish between the substrate and the cells. And secondly, you want to investigate different cell lines. And lastly, we want to try to stain the cells to sort of investigate whether it's an optical problem or whether it was a morphology problem. And I think as Kat's already touched on, these are only the two specific applications we explored. But I think the ability to measure transparent materials in a 100% inspection environment is huge. And thank you. And we'll take some questions.
Wondered whether the transparency would be the problem that you didn't detect the cell counts.
Yeah, I can clarify that a bit. It might not. Oh, sorry. I can clarify that a bit. It might not be, it's probably not, sorry, the transparency of the cells. It might just be the optical properties of the cells. They might side scatter a lot of the light that comes in and not reflect a certain amount back. We would have to do further experimentation to see if this even is an issue. So like we said, we would stain the cells and see if that changes the optical properties of the cells so that we would actually be able to detect them. So if we are able to detect the stained cells, then we know that it's something to do with the optics of the actual cell, which is something that has not been really thoroughly researched. So then that would pose a lot of problems, because obviously we don't want to stain cells. We're trying to go away from that and make it a non-terminal procedure. So if that is the problem, then this might not be an application for FocalSpec's LCI-1200. Whereas if we can't measure the stain cells as well, then it might be something more with the morphology of the substrate or the reflectivity of the substrate. So that's kind of where those future considerations are taken into. Does that answer your question?
In for your depth measurement and width, what is the resolution?
So the Z-height resolution is 550 nanometers. So yes, that's the resolution of the sensor. The wavelength is a spectrum of wavelength, right? It's in the visible spectrum. So it correlates, so it actually focuses each wavelength on a specific Z height. And then we can measure the highest intensity of each wavelength and correlate that to the Z height. So the Z height can achieve to 550 nanometers.
And so presumably that varies depending on your field of view and your magnification.
Right.
So you could alter those.
Right, it's all in the optics, right? It also depends on the line profile length and the pixels, right? Because the line is formed by individual pixels, and there's a distance between each pixel, so that also limits your resolution as well.
Right.
Yeah.
Okay, so can you, how do you distinguish a reflection from the front surface and a reflection from the back side, or some
Interesting. I think
feature?
so it's interesting because this sensor can actually detect multi-layer things. So if you have a PDMS that's really thin, it can actually see both the top surface and the bottom surface. I don't think it can detect the back interface. Are you talking about the light reflected from the...
Yeah.
Right. I don't think it can do that. So I think the only thing it can do is the top interface.
So if you're working on the assumption that the back interface is going to be so far out of focus it won't contribute.
No, we can actually extract which layer that you want, right? So,
Okay.
for example, if you have PDMS flat and then you have channels within the PDMS, we can see both the top.
That was my next question.
Okay, we can see both top and the channels within the PDMS, and in the software algorithm, we can actually extract which layer that you're interested in.
Okay, very
Yes.
good. So I didn't understand what the principle was when you were looking at cells. Why do you believe you should be able to see cells?
Sure. Do you want to answer that question?
I can try to.
I think for confluency, there's two approaches, right? The first is the confluency, the second is the apoptosis. I think there's two things that we're looking for when it comes to cells. The first is morphology. If we can physically map the cells in X, Y, Z.
Yeah, the difference in refractive indices is pretty small.
So, right. But we're thinking if we can just have the cells on the substrate, then we may be able to see maybe a bulge when the cell comes out, maybe a couple microns, because the resolution is submicron. So we're expecting to see a morphology change, right? That was the first approach. And second approach, it was intensity. And I think that was more of a secondary goal that we had in mind. I think the intensity comes more in play in apoptosis when the intensity changes more. But
Do you know that? Or
Yeah, so when cells go through apoptosis, they increase in granularity. So I'm not the cell expert, but that will increase side scattering when you shine light on it. So then there'll be less reflected light. So therefore, the intensity will be less. So that's the theory that we took to that approach. And that's how we would be measuring the apoptosis, like determining between an apoptotic cell versus a healthy cell.
yeah, our cell expert is actually with the poster.
Yeah.
He's the one who did all the research.
Yeah.
I think.
Yeah.
Okay, I think we're out of time, but thank you.
Okay,
Perfect.
Thanks
Thank
for your
you.
time. Thank you.